So, in this video, we will be solving 4 different types of one-step equations. The video might get a little bit long because I'm going to do 1 or maybe 2 of each examples, but I'll include time points or kind of reference points so that you can jump to whichever one you need to see. Okay, so we're going to start right in with these one-step equations that indicate addition. That means they look like that it says x plus 13 equals 24. So it includes an addition sign, but we're actually going to solve it by using subtraction. So the goal here is to isolate x to get it alone, so we need to eliminate this positive 13, and we do so by subtracting 13. We need to bring in a negative 13 or subtract 13 from this side of the equation. Like we will do in all of these, whatever action we perform on the left side of the equation, we are also going to perform on the right side of the equation. And the equation is divided by the equal sign. So left side over here, right side over here. I subtracted 13 from this side. I need to also subtract 13 from this side. These cancel. There's no need to write zeros down here. It cancels. Because positive 13 and negative 13 are opposites, and that they wash out to 0. 24 minus 13 is 11. I like to bring the equal sign right on the line. Keeping neat with these and organized will be helpful. And I like to bring this x, well, not like to, you have to, bring this x down. This is a completed equation. Okay? This is the first example of addition. We're going to do this example next because the difference between these is that it involves some negative integers. Which means that we're going to have to take a look at how those integers interact. So, like I said before, these look like addition problems. They're solved by subtraction. However, you need to be flexible, and you need to understand how these negatives in this problem are going to affect the way that we perform it. So, here again, we're trying to isolate x. What we need to get rid of is this negative 2 by doing its opposite. So basically what I need to bring in is a positive 2 here. You need to look at these two signs and evaluate and say, are these opposites? Am I doing an inverse operation? So yes, I am doing an inverse operation. Whatever I've done here, adding 2, needs to also be done here. Just like up here, as these were opposites, they canceled. These guys cancel, and now I need to deal with this. Negative 9 plus 2. In my head, I say to myself, negative 9 plus 2. I like to visualize it left to right as opposed to up and down. When I see it left to right, it's easier for me to remember that this is negative 7. So negative 7, x is isolated and alone. Let's bring it down. X equal sign right on the line. I like that. X equals negative 7. This is another completed example. If you look at them kind of from a distance, they look the same. There's a line dividing, a little table drawn by these two lines. Everything is kind of kept consistent. That's important when you do that. Alright, on to one of these examples. These, I'm only going to do one. They're almost exactly the same as these addition problems, but the original problem just has a subtraction sign. So if I show this to a group of students, or I'm explaining this, and I say some mystery number minus 10 equals 22, I usually have someone who jumps out of their seat and says, I know what that is, it's 32. And what I'll do is I'll say, okay, so you think x equals 32. Let's find out how to get there. So x down here at the end of the day, at the end of this problem, is isolated and alone. Up here it is not isolated and alone. It has negative 10 keeping it company. So we need to do the opposite of negative 10. That's positive 10. So here we go. Positive 10 and positive 10 on this side. These cancel. X has been isolated, and 22 plus 10 equals 32. So this is finished. And I say to the student who shouted out the answer, you're right. These are the steps, however. We need to see those steps. So I'm not going to do another of these. We don't need to. So if you follow steps that look like this and you're performing the opposites, like adding 26 to this and subtracting 15 from here and adding 24 to here, and I'll do this one in mine as well, adding 8.3 to here. If that's your first step in trying to isolate the variable, you're on the right track. Okay? Two more, multiplication and division, and I'll do 2 of these multiplications, and we really only need to do one of these division looking problems. Okay? So We'll take a look at this first one. It is fairly easy. I present it the same way I presented this one, and I would say to students, 7 times some mystery number equals 14, and someone is going to shout out, x equals 2. And I'll say, you are probably correct. Let's find out. So, the problem looks like multiplication. We have a coefficient, the number attached to the variable here, times the variable equals 14. 7 times x equals 14. I'll ask, what's happening to x? We're multiplying it by 7. The opposite of multiplying by 7 is dividing by 7. Okay, that is our first action. We will divide by 7 on both sides of the equation. This 7 divided by 7 equals 1, and 1 times x equals x. That's the real explanation, but really what happens is they cancel. That's the way that you can look at it. That leaves x totally by itself, and we ask the student that shouted it out, what is 14 divided by 7? And they say 2. So this is all correct. They were right, but you need to show that you're dividing both sides by the, right here, by the coefficient. Okay? Becomes more important on a problem where the division is not even, meaning the answer is not a multiple of the coefficient. So let's take a look at this one, because this is one of those cases. Same steps. To solve this, we need to divide both sides by the coefficient, but in this case the coefficient is -5. So the real problem that we have to deal with is 17 divided by -5. So these cancel, and I would encourage my students to, let's take a closer look at this problem. I would encourage my students off to the side to actually write out this problem in long division. I think it's most easily done that way. 17 divided by, call it -5. How many groups of 5 can be taken out of 17? Students should be alright with this. We've practiced this. 3 times -5. I'm going to leave the negative out of it. I just need to remember that my answer is going to be negative. 17 minus 15. This is to find our, what we used to call a remainder. Now we need to handle this remainder of 2. So we can turn our remainder into a fraction. The remainder becomes the numerator of the fraction, and the divisor of 5 becomes the denominator of our fraction. So the real answer here is 3 2/5. Whatever, let's skip back, whatever this division problem equals, this 17 divided by -5, whatever it equals, that is our answer. So x is equal to, it's very small, but -3 2/5. Glory. That's quite a problem. Now, that's pretty much it for these. You're always dividing by the coefficient. So just like I did before, you'll be dividing by 11, dividing by -4, dividing by 25 over here, dividing by 3. This is another one. Put a little star on that one. This is another one that 3 does not divide evenly into 8. 8 cannot be broken up into even groups of 3. So you'll end up with some fractional kind of remainder on this one as well. Here, division. These look like division problems. Anyone who has me in a class will see this. I'll write it here so that it's a mnemonic that helps you remember that fractions are division. Fad. It's not just a fad. It's not going away. This looks like a fraction. Y over 3. We have a numerator. We have a denominator. Fractions are division. So these problems involve division. They will be solved by the opposite, the inverse operation of multiplication. Multiplication, division, opposites. Addition and subtraction, opposites. So we'll be multiplying by the denominator. That means the number obviously on the bottom of this fraction. We need to multiply both sides by the denominator. So we multiply this left side by the denominator and the right side by the denominator. This, just like in all other examples, cancels the whole numbers that are on the left side of the equation, leaving us with just x. And x is equal to 8 times 4, whatever that is, 32. I'll tell you that when you multiply by 4 on both sides, it cancels the whole numbers. So the first steps would look like this: times 3, times -5 times 20 times 7. Those are the first steps for each one of these, okay? What really is happening is a little bit more complicated. When you multiply this fraction on the left side by +3, you're actually multiplying by 3 over 1. And you're multiplying this fraction times this fraction, which, if you multiply these fractions, you would just multiply straight across, and you'd have 3 times y and 1 times 3. That turns into 3y when you multiply the top, and 1 times 3 is 3 when you multiply the bottom. The long story is that 3 divided by 3 in this fraction here is equal to 1y, and 1y is the same as y. So all of this is going on when you say multiply by 3, or you say multiply by 4. It's quick and easy to say that it cancels the 3's and isolates the y. Okay? It can be a little complicated to understand all of this, but really what you want to say is when you so in this example, if I multiply this left side by 20, it cancels the 20's. And I have r equals 5 times 20, and that is 100. Okay, these are examples for one-step equations, addition and subtraction, multiplication and division, how to solve them in a neat and organized way that will help you keep track of your answer. So if there are any questions, you